Welcome back to this afternoon's session, our last session of the day and of the conference. Thank you very much. So yeah, before we get going on our final session, I just wanted to touch a little bit on our polls that we've had going on Slido. So we've had one that's finished. What do you see as the #1 priority to drive leakage improvements in AMP8? So I think some interesting findings on here. So smart metering coming up. We've got smart meters as well. So I think I'm going to award that as the winner. But we've got others on there: funding, doing the basics right, asset renewal, and so on and so forth. So yeah, interesting to see that. So thank you for that. And just a reminder, we've reopened the poll that we opened yesterday. Do you think the industry will hit the 50% reduction target by 2050? So we've had 2 extra votes so far. So I'd encourage you to all vote on that, and we will come back to that at the end of the day. So there you go. Keep voting. Keep voting. Yeah, and we'll come and see where that lands. But yeah, there must be at least 150 people in this room. So yeah, log in and give us your vote. Right. So the focus that we're turning to for our final session is on upstream leakage. And this is an area that, of course, is going to be a key focus for our teams in the next AMP. We're being challenged by Ofwat to be more proactive in this area. And there is an expectation for us to move away from BABE analysis. So there'll be a lot to explore and share to ensure that we have an appropriate and consistent approach. So we're going to start this afternoon's session with a presentation that brings us the latest experiences from Scottish Water and some of the methods they have used, working in collaboration with Xylem, to address trunk main leakage on both the mainland and in some difficult geographies such as the Shetland Isles. And we were having an interesting discussion over lunch about some of your geographical constraints. So yeah, I'm really pleased to welcome Sandeep Bhatt, Condition Assessment Engineer at Xylem, and Ian Dunsmore, Technical Team Manager, Strategic Water Infrastructure at Scottish Water, who are going to take us through from detection to prevention, proactive management of trunk mains leakage.
Good afternoon, and thank you for the opportunity today. So Ian and I are going to be talking about detection from detection to prevention and how we proactively manage our truck mains in Scotland. So trunk mains, we all know the trunk mains, how critical they are. I don't really want to tell everyone what they already know, but we do want to remind you that these trunk mains do leak, but it's these small hidden leaks that we really want to focus on, because these are the major contributors to our non-revenue water, and it's these small leaks that eventually will turn into pipe failures and pipe bursts. So how do we address these problems? Well, looking at this chart, at the minute we are using effective methods to detect leakage, but when we start looking at a larger diameter pipeline, so 400 mil diameters and bigger, we really want to be inspecting these pipelines with inline inspection tools. These inspection tools can detect leaks up to 4 times more than our traditional methods. So let's explore some of our inline inspection tools. Firstly, we've got the smart ball. Some of you have heard about the smart ball. It's been around for over 18 years, and we've inspected over 16,000 kilometers of pipeline globally. It can be inspected, it can inspect long runs and in a single deployment. Key features are, it's got the acoustic detection, so we can identify and locate these hidden leaks with very high accuracy. It also has a metallic capability, so we can identify any undocumented features in our pipeline and confirm pressures on a pipeline, but also has the gyroscope capability, so it has the it can confirm X and Y coordinates in our pipeline. And during inspection, we can then live track the ball. So this is just one of the examples how we insert the smart ball and extract it. It's supposed to be only one ball in that pipeline. What we do, we install sensors along the pipeline, just over there, tracking sensors, so we know where the ball is at all times. So moving on to the pipe diver, now again, this is an inline free swimming inspection platform. But but it's more an advanced pipeline condition assessment tool. It's used to now know the condition of your pipeline and the strength of it. Used mainly for pipelines when we can't take the pipe out of service, but what we get, so when we use ultrasonic signals, so we can identify the wall loss for metallic pipes and provide a heat map just like this one. We can inspect concrete pipes, so we do use electromagnetic technologies even, to detect wire breakage. Used for clean water and wastewater applications as well. But what do we do with all this inspection data? Well, we gather information and all our inspection data, and we turn it into actionable recommendations for our pipe owners. So we gather the pipe diver and smart wall inspection data together with TMP data, profile drawings, all our loading conditions, pipe specification. We gather all this information and we use our historic industry data. We combine it together and we model it to produce our FEA curves like this. And so what we do, we plot pipe by pipe stick on this pipe curve, so we can then determine where it lies with our strength limit or yield limit of the pipes. But most importantly, we can get our remaining useful life out of these pipes. So we can provide the pipeline management strategy for our pipe owners. Now this is now moving on to like the prevention stage and really, providing so our pipe owners can then prioritize repairs, recommendations, but also do further inspections, and we can recommend other monitoring devices, such as our next slide here. So just to touch upon this is our soundprint AFO, which is an acoustic fiber optic. What we do, we insert cables inside our pipeline to detect wire breakage for PCC pipes. This is an inline continuous monitoring device, so it gives us live data. We can capture this data in a DAC, and then this information is then passed on to our analysts, which with the aid of AI, we review it, and then precise location data and everything is passed on to our online portal, so our pipeliners can actually see this. Ian's going to be talking about this device or this project, so we've used one of these in Blair Linens in Scotland. Next year, we're going to be rolling out the leakage detection for AFO, so that's exciting. And but lastly, I just want to say that we really recommend all pipe owners to install something like this or consider to install something like this on their pipelines, especially when you're installing new pipelines. The costs are minimal, and we can install it on the outside of your pipeline. Okay, I'm just going to hand over to Ian now.
Thanks, Sandy. Ian Dunsmore. I'm the token Scotsman presenting this week. I'm a DEI hire for diversity, inclusion, etc. In Scottish Water, we work a little bit differently than you do down south, as in that we have different owners, different regulators. What we agreed with our regulators is, rather than in previous investment periods, we would have named projects that we were going to deliver, and then if you wanted to change one of them, it was quite an involved process to do that. So what we did this time around is we've agreed management approaches. So I look after a management approach which manages trunk mains, raw water mains, aqueducts, tunnels, subsea mains, and critical valves. Or as I like to say, all the stuff that when it fails, you end up on the front page of the paper and your CEO's in the news. So what we have is, from the management approaches, we'll have these kind of matrix set up. So we will assess the impact of an asset failing, the likelihood of that asset failing, and then depending where it sits on that matrix, tells you whether you do or you don't do something about it. Excuse me. So the likelihood of failure for trunk mains and raw water mains is based on asset condition. It's a kind of remaining service life, as much as that is an incredibly flawed calculation. It's about the only one we have at the minute, but the remaining service life dictates what the likelihood of failure is for these assets. If anyone's of a nervous disposition, I'm about to show some burst pictures. So, this is Auchenhowie Road in Glasgow, April 2023. Our best estimate is around 5,000 litres a second coming out of this burst when it happened. I say best estimate because our telemetry tops out at 5,000 litres a second and can't record more than that. So it could have been a bit more. The reason this is particularly prevalent or particularly important today is we have since sent that pipe away for analysis. We know what caused this burst. And this burst is actually what caused me to submit to UCWR the very poorly named project that Elizabeth's been unfortunate enough to get involved in about where we have road loadings and their impact on pipes, because we know this burst was at least in part caused by traffic loading. So what's actually happened here is the traffic loading has been stressing the pipe. The concrete lining at the 3 o'clock, 9 o'clock axis has cracked over time from this compression. That's then the only point the water can get at. The water has rusted those particular lines in the pipe, and that is why, when it failed, it opened up like a clam. You don't usually get a burst that most of the length of the pipe pops off like this. But the reason it did was we had high levels of corrosion along very specific points along the side of the pipe. Thankfully, a few hours later, it looked a bit more like this. But one of the actual saving grace of this burst is, if it had failed like a normal burst, on the left of it, the M3 is the one that failed. The one on the left of it is another 36-inch cast iron pipe called M4. The one on the right of that is called M2, and just underneath those cables is M1. So we have 4 36-inch, 160-year-old cast iron mains in the same street, and based on that's probably about a 6-inch hose that's in there, probably about 8 to 10-inch gaps between the pipes. So if that one hadn't gone in such a catastrophic way, it would have probably taken some of its neighbours away with it. Again, tying this back into yesterday's conversations, we talked about how difficult it is to reinstate around pipes. You've got an 8-inch gap, how are you getting proper compaction and the reinstatement underneath that repair once you've done it? But again, if we'd inspected that pipe, we would have seen the cracks in the cement lining. We could have potentially gone in and done something to prevent it. So we've actually already raised a project to go in and camera the other 3 pipes in that road, because if 3 has been experiencing traffic loading, there's nothing to say 1, 2, and 4 haven't as well. These beauties are 48-inch cast iron pipes on about 170 years old. The burst on the left's from 2003, the burst on the right's from 2021. But if you look at the actual burst itself, they're practically identical. These siphon pipes failed because of bell shear failures. So the pipes have become unsupported, you've put a bending stress on the joint, and eventually over time that weakens and a third of the socket pops off, and you end up with a massive repair. Every repair on these siphons costs me in the region of about £1 million to repair. 100 to 150,000 of that is the cost of running the pumps that we need to pump, rather than using the gravity supply while we repair it. But again, the reason these pipes have become unsupported is there would have been small leaks there. The leak has washed away the support around the pipe has become unsupported, and it's failed catastrophically. If we'd found the small leaks, if we'd fixed the small leaks, I would be at least £2 million better off. At the minute, we've had a bit more than 2, but these 2 pictures showed exactly the same kind of failures. So in terms of preventing failures, we mentioned about the work, smart ball. We've done a number of smart balls in Scottish Water. We did one up in Shetland, as was mentioned. We actually found a leaking air valve on that smart ball inspection, so we did kilometres of main in one go, found a leak nobody knew about, fixed it. This particular example is from Fife, a bit closer to my home at least. And when we did the smart ball in this trunk main, we found a leak, passed it over to our operations colleagues. They went out, dug down, found the leak, repaired it. It was a small leak at a connection for a service. Because we've gone out and repaired this when it's a small leak at a connection for a service, we've potentially prevented one of these from happening. So this is more what we need to be doing with the trunk mains, is getting out there, finding the small leaks when they're small leaks, because I'd much rather spend £30,000 fixing that than £1 million fixing that. Might be my Scottish nature, but I think probably most of you would agree with that. I'd rather spend 30,000 than £1 million. So in terms of the Blair linen system that Sandeep's already mentioned, we've done smart ball pipe diver surveys, overcame some unexpected challenges. If you want to know what they are, seek me out later. But the fun one was we found half a dozen bits of wood in the pipe from 1972. So obviously they'd put some wood in to jack the pipe to make it the right shape to put the next one on, and nobody ever bothered to go back in and get them. But why would you know 50 years later that there's some wood left from 1972? And can't really blame pipe diver for getting stuck when we've got a picket fence across the pipe like this that it had no chance of getting through. But it was worked with ourselves, WRCs, ILM. And the important part about this is the analysis of the data. That allowed us to target our next step. So we did a partial replacement of the pipe, but the main thing we did was spend a significant amount of money putting in this acoustic fibre optic system, but compared to the cost of replacing 16 kilometres of 40-odd inch pipe, it was pennies in comparison. And the beauty of that is that it means that now I can tell for every individual pipe stick which ones need work doing. I can plan work for that particular pipe stick and surgically remove one piece of pipe rather than replacing the whole pipeline. Now, in a land where we're not going to have money to be replacing pipes, if I can replace 3 metres of pipe rather than 16 kilometres of pipe, again, my Scottish nature coming to the fore again, but I would much rather replace one pipe than 3,500 of them. So this analysis is, there's hydraulic analysis about pressures. The finite element analysis is the key one that brings everything together. We have the design checks against what the material should be and is. We do calibrations because not all PCC pipe is created equal. And then we come up with this useful life analysis. So the good news was, when we surveyed this 16 kilometre length pipe, the vast, vast majority of it is fine. It's 50 years old, so it's maybe not as shiny as it used to be, but structurally speaking, 5 out of 5,500 pipes needed something doing with them. So we can go and do something about those 5. And then even over time, out to 2055, we're still only looking at 100 out of 5,500 will actually need work by that point. So spending this money doing these inspections, we can now get a much more lined up view of how we're going to do stuff in the future with it. So for the finite element analysis, what we've agreed is you have these different coloured bands and then the lines. So that strength line is one we never want to cross. So when a pipe moves from the kind of green into the yellow, we will create a work pack. This is how we're going to fix this pipe. When the pipe moves from the yellow to the red, or if it ever moves from the yellow to the red, we then action that work plan. So we're going out and fixing the pipe before it fails, but at the right time. So we're not fixing it too early, but we're also not letting it get anywhere near its strength limits. My team mailbox get emails most days. The vast majority of them are pipe number 2106 has gone from 1 to 2 wire breaks. So I really am not particularly, it's good news. It's only got 2 and it's got plenty of scope left. And what we've done is, as I've outlined, we've agreed these intervention levels. And if something catastrophic happened, like one pipe suddenly got 20 wire breaks overnight, chances are somebody's hit it with a digger, if we're being honest, because that's not going to happen naturally. Xylem will call our intelligent control centre, alert them to it. We have pre-prepared, putting my teeth back in, plans for how we deal with faults in different areas of the pipe. So they've got a document they can refer to. It's a planned emergency, if you like, and that we have a plan for the emergency. Thank you.
Thank you both very much. So we've got some questions online, and then we'll come to the room. So first question, what % of your trunk main stock have you been able to assess with these tools?
1% of our trunk main stock is concrete, but we've done quite a lot of that. We have currently over 100, I think we've got about 2,000 kilometres of our trunk mains that have either been inspected or we have scheduled in to be inspected in this investment period. Yeah. So that's about 20% of our trunk mains will have been inspected recently by the end of SR. Again, sorry, SR21 for me, you're all used to AMP periods, but 21 to 27 is our investment period.
Yeah, and I guess that last graph that you showed gives them comfort about how frequently you need to kind of get through that as well. So,
yeah. We're also developing on a statistical basis based on how many pipes of what materials we have. So we've got representative samples of all the testing we do, so that we haven't just tested cast iron or just tested asbestos or just tested. We should have a good balance of samples so that we know with a degree of comfort what our expected life is for the assets.
Yeah, brilliant. And the next question, which was from Katrina, have you managed to incorporate the growing climate change risks into your probability of failure assessment?
Indirectly. We have a number of different things we score. For the likelihood of failure, it is purely based on remaining service life at the minute for these assets, but we are looking at other things that can feed in there, like if there's pressure transients on the line. But we're going through the second version of our management approaches at the minute, and we're looking to incorporate more about that. Everything we do in Scottish Water has an element of climate change built into how we look at it. It's just not specifically called out in the document. It's more of a company-wide thing rather than specifically for trunk mains.
But increases your resilience anyway.
Yeah, I mean, if you can get the pipe in a good condition in the first place, it'll stand up to climate change better.
Yeah, brilliant. Good, right. Any questions from the floor? Or are you all asleep after lunch? No, I can't see any. So, okay, well, thank you very much. We'll move on, but thank you, Sandeep. Thank you, Ian.
Thank you.
Oh, yeah, sure. Right, no worries. Brilliant. Right, don't forget the poll. We're up to 78 votes. Could do. I want to get above 100. Come on. Right, so the next session, we're going to move into sort of a mixture of presentations and panel discussions, still focused on the theme of upstream leakage. So I'm going to hand over the chairing at this point to Paul Taylor, who's the assurance manager for leakage at Severn Trent Water, who's going to lead this session. And Paul will be joined by Ken Cartwright, associate engineer at Atkins Realis, Dilraj Dillon, director at Crowder Consulting, Ian Dunsmore, you're coming back, Michael Hurley, technical director of Tetra Tech RPS, Justine Ledbetter, head of demand management WRC, Mikkel Wilmot, leakage assurance analyst at Severn Trent, and Katie Walker, leakage data manager at United Utilities. So over to you, Paul.
Thank you, Jeff. This is going to go swimmingly, isn't it? You can tell. Right, so good afternoon, everybody. Yeah, we're going to carry on the theme of upstream leakage. And what I mean by upstream leakage, I mean everything upstream of the DMA, just in case you weren't sure. We're going to talk about reporting, as we said in the introduction, Ofwat are pushing us to be more proactive on our upstream network, moving away from BABE, burst and background estimate. And this is a big one for water company leakage managers, because this will be the first time in 5 years since Ofwat wrote the guidance for AMP7 that we will start to change some of the methodologies that are in that guidance, and upstream is the first one of those. And from what Ian was saying yesterday about a root and branch review of all of the components and all of the water balance and leakage calculations, that this really becomes the forerunner for that change. So it will be interesting to see how this gets adopted and how we move forward. As you can see, we're going to do things slightly differently this afternoon for this session. So we're going to have 4 short, sharp presentations interspersed with some discussion and questions. We've got a fair bit of time for this session, so plenty of time for questions from the floor. I'll keep an eye on Slido, and we will see how we go. So, first up, get things started. Ken Cartwright's going to talk about, we're going to set the scene for us and where we've gone from and to.
Okay, thank you, Paul. I'm glad you didn't nick my joke about S Club 7 reforming with our song, Bye Bye Babe, Babe Bye Bye. So, set the scene. I'm going to go back a long time to when I was a grad. Over 25 years ago, United Utilities identified as they were reducing DMA leakage, DI wasn't reducing and the gap in the water balance was growing. They wanted to know if there was a problem with trunk main leakage. So Upstream flow balances was developed, or as they're nicknamed, tiles in United Utilities. Some years later, they moved to reporting upstream leakage using flow balances in 2015, the first in the industry, and really a benchmark point. A couple of years later, Atkins were commissioned by UCWEA to complete a best practice into upstream flow monitoring zones. A lot of companies were involved in the steering group, and the study was issued in January 21. It covers many things because companies were in different positions. So we looked at the business cases needed to start up, setting them up, the validation, the reporting, how it's actually constantly learning and developing as you're going along, and the potential to report. So what are they? Although Paul's just explained, it's everything, every main, every asset outside of your DMAs. It could be trunk mains, it could be distribution mains which aren't within DMAs, it could be storage sites, it can be a mix of that. But basically the idea is you've got meters in, meters out, you can measure flow in, flow out, flow into DMAs. During the study, we were in COVID, it was quite interesting, but growth, home working and hot weather were starting to cause problems to water companies operationally, but also in their water balances. Trunk main failures was a key impact on interruptions to supply and property seconds being reported. On the back of this, we've actually seen more trunk main resilience connections being put in the ground without meters. If they were following best practice, as identified in the study, and had upstream flow monitoring standards in place, those connections wouldn't be installed without meters. The lack of meters is now causing companies even worse problems because they just don't know where the water's going sometimes. And that's causing a problem in a gap in the water balance, which I think Ian maybe alluded to earlier today. The key thing about upstream flow monitoring zones, though, it's not just about leakage, there's a lot more benefits. Just looking at how leakage is reported, I won't go through all this in detail, but trunk main leakage, there's 8 methods being used currently to report trunk main leakage. 6 methods for service reservoir leakage. 2 companies use flow balances on 25% of the network. Only United Utilities use flow balances across the whole network. BABE was the most common method used, which is obviously being retired. And the thing about BABE is you can sort of manage it quite well by how much effort you put into looking to leaks on your trunk mains, or even what trunk mains you are walking. It also doesn't like small mains outside of DMAs in the calculation. So what was it United Utilities did and what the study covers? Sorry about this, I took out all the quick stuff, but they set up what's called a strategic balance. So they realised that intermediate trunk mains and connectivity between trunk mains was causing a lot of uncertainty within the flow balances. So they took it back to principles. We know our DI going in, we know our water going into our DMAs. That's the number we need to reduce. And that's the number they sort of report off. What they do with flow balances is they split those strategic areas up into smaller segments, and that enables them to identify, is there an anomaly with our DI meter? Is there an anomaly with a DMA? Is there an anomaly with our understanding of demand outside? They know where that problem is in their network. Trunk main error connectivity can cause big discrepancies in the numbers you get, high positive and negatives. But the validation process they follow, which is really key, tries to iron those problems out. It tries to track down where can we tell where the water's going, even if we've got bad data. And that's quite critical, because where they find there's a problem with a DI meter or a DMA meter or demand, they feed it straight back into the strategic balance and reducing the unaccounted for water down to a more realistic number. The lack of metering across our network is really causing problems. And the method, although not perfect, it's trying to iron those out, it's trying to learn. The problem with software at the moment is the IT software, the leakage software at the moment doesn't do the validation automated in an automatic way. It's based on minimum night flow, it's not based on bulk volume. So the process is very manual, and it's down to the skills of the analyst who's actually looking at the data to iron out those problems. just to show you can get good balances, because I've been told loads and loads of times they never work. This is a trunk main. Bottom graph is what you see, really spiky all over the place. You zoom in, one thing you can see, it's got demand. Yeah. That demand is about 0.13 of a meg. There's only 180 properties apparently fed off that trunk main. So, you know, in the rules of the world, we should be estimating a lower demand. We know it's higher, so we put it into the balance, we put it into the strategic balance. We haven't checked our DI meter. We think there might be an offset. We haven't checked our bidirectional meter into a DMA, but we can tell there's leakage. So we've told somebody we think there's leakage. They've gone out, and to date, they've found one leak so far. This is about 3 weeks old. It's going in. On the back of the study, Atkins Realis got asked to form a Upstream a steering group. So to be inclusive, we don't charge for this group. Any water company is free to attend. We meet biannually, we talk about stuff within the best practice and things which were out of scope of the best practice study. We have guest talks from IT suppliers and leak detection equipment suppliers, and even Ofwat. And it wasn't our fault about what they put in for 2030. I think we convinced them that it wasn't going to be 2025. Yeah. The next session is going to be held in spring, and we're looking at how best to infill data, confidence, uncertainty, and operability. Now, just going to fill in the last bit, which is the best practice is actually about being proactive. It's not just taking data and looking at it and saying, oh, it's wrong. It's about being proactive and resolving those issues. This is something United Utilities did. They used flow balances. They had a number higher than what they reported at BABE. They took that number down to what BABE showed. They've taken it down further. They've done this by not worrying about uncertainty. It's unaccounted for water, not leakage. It's a number they don't like, and they need to improve it. Their focus has also justified investment. It's brought in other parts of the business. They've improved on production planning, operational awareness, and network modelling is really improving. And I will say, there's a bigger issue coming into the industry rather than just leakage. Yeah. That's 3 water companies' DI in total. We need to do things differently. And to be honest, if you don't like flow balances or you don't want to use them for reporting, they're still really useful to your company. And if making them used for reporting means they get invested in, I think it's worthwhile. Thank you.
Thank you, Ken. Atkins wrote the best practice guidance. Can you just be clear on the shortcomings of BABE, please?
Oh. I mean, I say it can be massaged, shall we say. So it's based on, you know, how many leaks you find, how much effort you put in. So if you're not putting a lot of effort, you're not finding a lot of leaks. So you get a lower number. If you use your new apprentices to go out doing leak detection on your best performing trunk mains, you factor that number across your network, you don't find many leaks, you get good performance, you get a low number. Not saying that's what happens, but that's what could happen. The other thing is, BABE is about reporting, that's it. Adds no other benefit to any water company apart from we get a number in a water balance to report on leakage.
Okay, fabulous, thank you. I think it's worth making that point, clearing that point up. Yeah. Okay. And so moving forward, flow balance is an option. Flow balances are an option. Is there anything else that you're seeing? Because a lot of companies are starting to look at flow balances, but they're all doing stuff in slightly different ways. Do we understand why that is?
So, yes. We've wrote best practice on setting up and managing upstream flow monitoring zones based on the data and the steering group at the time, a few years ago. Flow balances have been around for a while. Lots of people have come up to me already and said, oh, we used to do them years ago and they're rubbish. or they get negative back. So there's a few things. Previous bias. Yeah, people have used them, they either like them or they don't like them. We highlighted in the report the issue with the culture of using meter error, unmetered connections as a reason not to do something, instead of, as United Utilities has shown, is being proactive. You're learning about your network. There's also, I think, the data they have, the guidance they've been given, the leakage software they're using, it all changes how people think. So although we may have written the best practice, I guess consistency of leakage 5 years on, how consistent are the water companies are reporting leakage now?
Okay, thank you, Ken. We shall move on. Thank you. Have a seat. Right, so let's talk a bit more about reporting aspects of upstream losses, and Mike Hurley will come and talk about that. Thank you.
Thank you. Afternoon, everyone. I'm going to talk a bit more about upstream leakage in the context of the reporting side of things. Obviously, Ken's alluded to the fact that there's a targeting view and a reporting view, so I'm going to talk a bit about the reporting view. Just use the picture from a trip near my house just to show that trunk mains aren't just about leakage and sites. There's assets on that trunk main that are worthwhile walking on occasions, just to see that your assets are still there, working and all available to be used. That is an air valve in there, if anyone wonders what that picture is for, but just to show you what it is. As several people have already alluded to, David's there, so we've got to move on from that point of view. What I'm going to talk about is really about reporting. We've got to come up with a figure. So ignoring the fact that you've got some areas that may or may not balance, it's about coming up with a reported figure. BABE was a reported figure, so we need to come up with a reported figure now using the flow balances. So the question I was posed as well is, are we reporting real losses unaccounted for water or total imbalance? In most cases, we're looking at the imbalance. We're trying to understand the volume of water. We can't really, that is the difference between these meters. So we're looking at volumes of water that are in imbalance. This is an anonymised graph. I've made sure that I've anonymised this graph. This is to show you some example of companies about how they may report leakage at the moment. I've purposely put indicative because this is not taken from any Ofwat reporting. It's to show you that there's companies with quite a lot of trunk mains there, and when we convert that and try and get into the size, this is a meters cubed per kilometre per day, so we're trying to show that spread of leakage across the network. And obviously it isn't just companies with lots of trunk mains that've got leakage. There's smaller companies with less trunk mains that've got higher leakage levels, so there's quite a spread. So there's clearly a challenge across the industry to understand how to report and how to move from where they are now with a figure to a figure using flow balances. So just to show you, there is a bit of a spread. Not everyone's on the same ballpark reporting the same figure. So it's just an anonymised piece of data just to look at there. Ken's already alluded to data being the key to this. We need flow meters, we need them working, we need to be able to calculate these balances daily, weekly, yearly, and come up with that. So it's coming up with a suite of tools to do some validation on that. I think Ken alluded to, there's still quite a lot of manual analyst work looking at this type of data. So we need to look at how can we automate that. So we've looked at some of the methods we already apply to things like DI and abstraction, where we're reviewing that data and automatically putting data in when it's not available. So we're looking at different methods to do that. So we want to do that with flow balances. To a certain extent, treating the flow balances like DMAs. They're not DMAs, you're not targeting them in the same way, but you are trying to treat the data and the balance in the same way. You need that data in all the time. You need to understand that area as much as you can. I think the mention about unmetered connections, you need to learn about that network and doing that. You need data in front of you. So there's lots of different things of coping with that missing data. We then need to extrapolate these results. So I think Ken has shown a very good slide there, summing all these individual flow balances. So we need to understand where data is missing. Is it okay? Have I automatically filled some data in? But really and truly, I've got to come up with a final figure for a company. So I've got to put that data all together for all of the zones to get that coverage up. So it can't be just a sample set. We really need to extrapolate that out to a company level reported figure and crack on with that. There's obviously, I've mentioned talking about them in the DMA sense of the word. We've also got to think about that availability and operability. You know, do we understand every trunk main we've got? Are they available? Can we report on them? Courtney's done some good examples of, we need to know about these areas. Do we know enough about these areas to be able to report them? And we've got to treat that in the same way we're doing with DMA. So this is just anonymous sort of stats on coming up with a figure for trunk main availability and operability. So we need to have something to report on alongside the actual figure. So you've got a figure, but what sort of availability and operability you're talking about in your trunk main data set, and how are you improving? Because it's going to be a journey. Not everyone's got all the metering available at the moment, so it's going to be a journey to see how you can improve along there. This is a bit of a good example. I've tried to anonymise it, but I can still see something on there. But I've tried to anonymise this example from a company of a lot of these balances can be challenging. So there's an inflow, and we've got 7 or 8 outflows. That black line at the bottom is the balance. So that's not far off, considering all the meter errors across that, of getting a pretty good balance. So the team can get pretty good confidence that they do understand the metering. There's a hint of a diagonal profile, but that's pretty good in the tolerance world to say, actually, we don't think there's a big discrepancy here. We're quite confident in the figure that we can get. So it's just to show you that there's a lot of people who are looking at these balances at the moment aren't getting good results. They can see the data, so it's all good. The other link to there is really Justin's going to talk about uncertainty in the data, so we can come up with a figure for how confident and what's our certainty in the figure that comes up.
Thank you, Mike. So these systems that you talk about, are they all fully formed? Are they fully evolved? Got all the thinking, all the logic? We've got WaterNet here. We've got NetBase on the stage. Dill, you can respond as well. Are they all ready to go, fit for purpose?
I think the data's all there. Sometimes it's the conglomeration of that data and building in some of that uncertainty and confidence of the figure and setting your own views on what is operability and availability with your trunk main areas. So we're not fully there. We appreciate that, and we've tried to garner some feedback from some of our users. But I think all of the data is there. We've just got to put that together to present that final figure.
Fine. Thank you, Mike. Dill, any view?
Yeah,
Shane?
we've made quite a few strides in the last couple of years working with obviously yourselves, Yorkshire Water as well. So we've actually productionised our solution, starting to get used. It's in the state of becoming. We've still got quite a lot of things that we need to develop. And because we've got some guidance from the work that Atkins have done in terms of how we should report on the figure. But we need, as like I said, we need some feedback to say how can we get it to a point where we can trust the figures from the floor balances and not just say, you know what, these don't look right, we're not going to use them. Because eventually we are going to have to use them, so we have to do something about it. So I'm going to cover what we can do about it in a short while.
Okay, fab. Thank you, Mike. Thank you. There's a couple of questions on Slido, which just going back around definition. So do you think we should have a consistent definition of a trunk main? And there was one before, I think got cleared off around a consistent view of what a trunk main is. Is it based on size, type? Ken?
It was a big topic in the actual study, which is why we got to upstream areas, upstream, trunk main in a lot of the previous reports are big pipes.
Yeah.
Simple, they are big pipes. Anything less than an 8-inch isn't a trunk main in the old definition. The problem is we have big pipes in DMAs. We have small pipes outside of DMAs. So we had to really change the definition to go, it's about everything outside of your DMA, not about pipe size or type of pipe or whatever. It's a pipe outside of your reporting mechanism.
Can I just give the above the frozen north view? Our regulator defines a trunk main for us. So a trunk main, according to Wix, is any pipe 12-inch or larger in diameter, notional, obviously. So it's not something we make a choice over. It was defined around about the time that Scottish Water was formed, I think back in about 2002. So we don't have a choice in the matter. A trunk main is told, we're told what it is. So that's what it is in Scotland.
Dale?
There's actually a legal definition of trunk mains in the Water Act. So we just need to refer to that. But I think in terms of reporting leakage, I know we refer to them as trunk mains, but it's the area outside of DMAs.
Yeah,
the official definition is it's the mains that transfer water from one storage facility to another. That's the legal definition. So let's not worry about the definition.
I've tried to stop referring to it trunk mains and just call it upstream.
Yes.
I'll ask one question about metering and then we'll move on to Justine's presentation. So Michael Wilmot from Severn Trent. A lot of us know you in the industry and you made yourself a very much a metering expert. So metering, probably the single biggest investment for Upstream. Experience in Severn Trent, is investment needed? Is actually there's lots of meters out there that we just need to bring back to life? What's the experience in Severn Trent?
Okay, so across the industry, I think to do the reporting, I think we've probably got enough meters in the sense of, you know, you've got your DI meters, you've got your DMA meters, so DI minus DMA minus your consumption, you can get an answer. Now that's really problematic for targeting because that's great that you've got a number, but you can't do anything with it until you actually break it down. So the question is, do we actually have enough meters to break it down? And I think for most companies, including Severn Trent, the answer is no, we don't have enough. So we take Severn Trent as an example. So service reservoirs, quite often on the trunk mains, outside DMAs. If you look at our service reservoirs in Severn Trent, only 40% of our reservoirs have both inlet, complete inlet and complete outlet metering. So we know we're short. And we know that if we want to be able to target a little bit clever, a little bit smarter, we need to put that investment. So in short, Paul, the answer is, for reporting purposes, technically yes, but to actually do anything of great use, of great value to move it forward, then for the industry, including Severn Trent, it's probably a no.
Okay, thank you, Michael. Right, I think that leads us nicely to talk about uncertainty in reporting with Justine. We'll come across to the...
Try not to trip over on the way over here. So hi, I'm Justine Ledbetter, Head of Demand Management at WRC, and I'm going to talk around uncertainty in flow balances, how this kind of adds quite a significant complication when interpreting flow balances. Also, the impact, as we've already heard, is quite significant from a targeting perspective and trying to make some of those operational decisions. And then also touch on the overall implication for reporting upstream leakage. So to do this, I'm going to use a bit of a worked example because it's going to be a bit easier, because kind of calculating the uncertainty and bringing all the elements together can be quite complicated, so I'm sure lots of you know. So I'm going to start with the top graph. That's just a plot of total daily losses in from a flow balance. So as you can see from this, it's pretty stable across the year, not too much change. And out of ease, we'll just say that this has an average across the year of 5 megalitres a day. So now one of the biggest challenges we touched on with flow balances is that meter uncertainty aspect. But because of the significant volumes that are going through these meters, what can be quite a low percentage uncertainty can be an enormous volumetric uncertainty. And so by the time you kind of you've got your water in, take off the water out, you sum up all of those uncertainties, get it together, it could be not a huge amount of balance, so not much unaccounted for water, but actually if you put the volumetric uncertainty against that, it could be way greater than that balance. So straight away, is there anything there to go to try and go at or not? In this case, once again, out of ease, it demonstrated by the error bars, the meter error is insignificant to the volume, just to make this a bit easier. So if there was nothing else happening at all, which would be lovely, then you could say it's not unaccounted for water, this is leakage. There's 5 megalitres a day, and it's got an uncertainty of 1%, according to the metering. So to validate this, what we do is we have a look and plot the diurnal pattern. Is there any consumption? And as you can see on this one, there is quite a diurnal pattern that happens across there. So the likely case is that there are properties that are being fed directly from the trunk mains. So after this, kind of look into GIS, and this is where it's really, really key to have your properties tagged to your mains. I don't think I can stress this enough. One takeaway from this, tag your properties to the mains, because this part of it suddenly becomes so much easier. So let's say we look at GIS, or we have the properties tagged to the mains, and out of that we find there is some non-household consumption, there's also measured households, and there's some unmeasured household. Each of those have their own uncertainties as well. Kind of through your investigations, you need to try and assess that volume of consumption using the best available method, whether that is billing systems, if it's your meter data management system, if you've got another system in place, or if you don't have any of that, then maybe it's going to be your company average. And then along with that, it's that assigning an uncertainty to that element as well. So that could be from your kind of company-wide water balance. But suddenly, as you add in each of those aspects and you layer the data up and you incorporate that uncertainty, suddenly that very nice, there's 5 megalitres of leakage and it's got a 1% uncertainty, you've ended up with a 0.7 megalitres of leakage and the uncertainty is 26.5%. So suddenly it's a lot harder to actually make any operational decisions based on this. So from like a targeting perspective, this is where having that understanding of your meters, the meter uncertainty, and also understanding consumption and any uncertainties around that as well is really important, and trying to minimize that. So then finally, scaling this up to a company-wide upstream leakage point of view. Over the past AMPs, we've touched on kind of the lack of investment that there has been on operational meters. So that's meant that quite often there are some areas of the network which, if you're doing this bottom-up view and trying to create these individual flow balance areas and tiles, they're just not balanceable at the moment. So if you're trying to do this bottom-up view, you suddenly have your balanceable areas which could have quite a low associated uncertainty because you know that meter error. However, the unbalanced, there's so many different ways you could try and estimate that. You just have to infill it. So that's going to bring a whole new level of uncertainty and massive uncertainty, because depending on the method you use, you could span it, if it could be a tiny volume or it could be an enormous volume. So kind of have to try and capture that. And so that also has a massive implication on the uncertainty. And really, until these challenges are resolved, we touched on it in the previous presentations, really the idea, or the best case scenario for now, from this point of view, for reporting would be doing that DI and minusing your DMAs, reportable DMAs, because we understand the uncertainty a lot more. It's much better understood, and the consumption into the DMAs is a lot better understood, and also with the requirements in DMA operability and availability, alongside kind of the verification programs that are required for DI meters, it can try and limit that. And so you can see the differences in the uncertainty, the difference between, if you just do it on the left-hand side one of having got the same amount of leakage in both examples, but difference of 24.5% to 8%. Uncertainty, or 9% uncertainty. So over time, maybe as we improve our operational meterings and also increase our understanding of upstream consumption, we might be able to transition to a more bottom-up approach for calculating upstream leakage using flow balances, so moving more into the method that we do to calculate DMA leakage at the moment. However, for now, I think the key thing is we just need to focus on improving that operational metering and gaining that in-depth understanding of upstream consumption. Yeah, that's everything from me.
Thank you, Justine. Give you a chance to get back over there.
Thank you.
Thank you for that. So you mentioned targeting and operational meters. So where there's a lack of, Michael says for targeting there probably isn't enough meters. Is there anything we can do with the flow balances?
Yes, sorry, I just thought I'd try and stop anyone from tripping over them. So I think we have a lot of data available to us now. In DMAs, we see a lot of kind of leakage hotspotting and that type of thing that we can do using GIS data. We've had some quite good results of doing a similar kind of criticality style assessment of kind of looking at your cohorts of data, looking at the burst history, looking at the performance history on the different cohorts of material type, age, and that side of things. And then once you start layering the information up, you can make that decision as to, it can help narrow down if you've got in a massive area with where maybe no balance, or a significantly large balance but over 60 kilometres, which isn't massively helpful, then you can try and use that to help narrow it down. And if you combine that with the locations of your meters, that you know that there could be some improvements, you can make that decision as to, do you improve the metering in that area first to narrow it down? If there are already sites that have a meter, it just needs some fixing, needs a fix, or can you just use the GIS criticality side of things?
Okay, thanks, Justine. Before we go on to the next presentation, we'll pause there for questions. There's a few on Slido. Ken, do we know nationally what the proportion of total leakage on Upstream is? Put you on the spot.
Can I ask a question to you?
Please.
So the one thing we've done the Upstream work group, the one thing I've picked up on is we've had 14, 15 different companies attend. They're not very forthcoming to go, this is our number. Not all of them. They're still a bit scared. And I do wonder if we could get some anonymity from Ofwat to say, let us open the door, let's put the numbers on the table, because we can then get that number properly.
Do you want a mic?
Hi, thank you. We did do an information request back in IN 22, which looked at some of the leakage components. One of them was trunk main leakage, and you forgive me, I can't remember what the number is off the top of my head. I would imagine that we wouldn't have a problem with sharing that anonymously, if that would be helpful. I also am minded, again, you're holding me to it now, there is a very clear guidance at the moment in terms of what we would expect in terms of annual review if the volume of leakage, 5% off the top of my head, it's either 5 or 10%. You know, if it's more than that of your total leakage, we expect the number to be reviewed annually. Again, forgive me, I can't remember the number off the top of my head, but there is something in there at the moment. You know, and I think that's one of the things that will be brought out of one of the things that's driven the need for the review, and one of the things that will come out from the review is that you know, there's a huge amount of effort gone into DMA and distribution leakage, probably at the expense of trunk main leakage. You know, and now's the time to redress, pardon the pun, the balance.
Yeah, and I think as somebody says on here, trunk mains leakage is reported in the APR separately, which I think that's. Yes, whatever methodology people are using at the time. In Severn Trent, it's 14%. Katie, do you know in UU what your proportion of total leakage is? Put you on the spot, sorry.
Don't know.
Okay, question, oh, John, do you know? It's under 10%, thank you very much. Mike Dill, possibly, do you think data uncertainty should be accounted for in the balance software, or should raw data be adjusted?
Yeah, we prefer to hold both, so you can look at both.
Yeah.
It depends what the monitoring issue is. If it's a long-term issue, then you want to use one method. If it's a temporary thing, then you can estimate. So, yeah, both.
Okay, thank you. When you do a balance, should the whole imbalance be reported as leakage, or should it only be counted if greater than, say, 3%? I think it's coming back a little bit to the definition of, is it a total imbalance, is it losses, is it UFW, unaccountable for water? Any thoughts on that?
I mean, the way it's done is, yeah, if you've got a gap between your water in, what you're saying is demand outside the DMAs and water going into DMAs, that's the number. The validation tries to tie that down and improve that number. If you can't, then it could be anything, that's the problem, but you don't actually know.
Yeah, okay.
What we need to explore is the method that United Utilities are using, where you've taken the DI and the DMA demand. So you've got one figure there, you've got your flow balances, and that's giving you a discrepancy. If you aggregate that up, and we do a comparison between the two, and this is something we need to work out, and we compare those two, and say if they're within a tolerance, then that gives us confidence to say, yeah, we can take that number forward.
That's what best practice is.
Yeah.
So you mean a water balance, you're doing strategic balance as a water balance, not DMA versus DMA meters. So there's a difference.
DI against DMA.
Yeah, sorry, DI versus. So there's a difference of DI versus DMA meters and DI versus demand DMAs. And that happens because of operability checks within the software. So you can have a perfect good meter flow, but the DMA operability checks will overrule that data and put a different total daily flow. So that's why, correct me if I'm wrong, you go off the meter data, not the DMA demand data. But it is a good check.
You just got to be careful, because then you're contradicting what you've reported for your bottom-up leakage.
Sounds like some different views. That's the point. That's the point. That's the point of having the panel discussion. Katie, you were going to add.
Yeah, I think the key bit is that you're getting the tile balances, the total, whatever you call tile balances, water flow zones, something like that.
Yeah, UFOZ.
Those should add up to the difference between your DI and your DMA demand. So when those are all added up, yes, you might have discrepancies between one tile and the next tile, but when they all added up, then you are getting true upstream leakage. And we've got a lot better confidence in the true upstream leakage, the total, than we have on any individual tile. So we have quite a lot of uncertainty on individual tiles that is a bit of a snag for targeting, but in terms of reporting, because you've got DI minus DMA, then you've got a lot more confidence because you've got verified DI meters, you've got DMA meters that you can check against Paradigm. You've got a lot more confidence in that you are reporting a genuine figure with a lot less uncertainty than any individual small tile.
Okay, have we got any questions from the floor before we move on? No? Okay. Okay, Katie, let's move on from reporting a little bit. Give us some hope. United Utilities have been doing this a long time compared to most other companies, upstream balances. I don't know whether there are now some quick wins, some low-hanging fruits that we can all expect to get in the near future.
I think when United Utilities first started on the tiles, they started on this upstream journey and broke it down first into what we call demand monitoring zones, and then down into tiles below that. And when we went through that whole configuration and sort of network understanding, our upstream leakage reduced really quite significantly around our network understanding, And it meant that we actually did have some really quite significant big wins in the early days, where we narrowed down quite a significant trunk main leak that had its own little lake in the Burnley area. And when that lake dried up when it was fixed, then yeah, there was some quite big wins that we would not have known about if we hadn't gone down the whole setting up and the configs and the tiles and that side of things. What we are finding now is that the early days gives you the really big wins. When you're looking at that sort of quantity of water, I've not got any of my individual demand monitoring zones has got that sort of quantity of losses that we found in the early days still to go at. So I know that I've not got that sort of opportunity actually out there, but I am managing to find that by actually going into sort of super analysis on some of these tiles, we are able to actually go out there and do some proactive detection, and we are getting results in terms of not huge, not big, massive trunk main leaks, but we are getting quite a few of the leaks that are on the unmetered feeds that are directly off the trunk mains, on the fittings, on the joints. We're not finding the biggies anymore, but we are still managing to bring that upstream leakage down. We found reservoir overflows, we found things like that, that we are still finding stuff, and it is being able to actually drill down into the tiles that is enabling us to still go out there and keep driving it down.
Okay, thank you, Katie. You mentioned reservoirs at the end there, and I had a question for Dill, because you mentioned this to me before. How important are reservoir losses in this whole process?
Yeah, it's been surprising over the years that we've done this type of work for companies. The number of leaking service reservoirs we've found, it's almost more than what we found on the trunk mains in some instances. So don't just think about losses on your trunk mains. You definitely got losses on your service reservoirs as well. So they need to be looked at just as much as your trunk mains.
And are they infrastructure or are they overflows? And
they're both.
Right.
So we've got instances of both. We've found the roofs of service reservoirs collapsed. We've had overflows, cracked walls, a variety of things. So yeah, don't treat them any less than the trunk main system.
Okay, fab. Thank you. I think back to Katie. We're moving the discussion on a little bit. Leak detection methods for upstream, are they fit for purpose?
I think that's an area that we're all struggling with right the way across the board. It's lack of fittings, it's the length, it's traditional DMA methods just don't work on trunk mains. And yes, we've got certain tools that we can throw at it. I think we really need to be sort of trying to find the right tools for the right trunk mains. I think historically we've done various bits with dogs, we've done satellites, we've done a lot with the trunk main correlators, and a lot with the sort of hydrophones, but as well as we've done Sahara and some of the inline stuff. So we have used quite a mix of techniques just to try and get what we actually need to do.
Okay, thank you. So we talked quite a lot about being led by the data. I'd like to just pick up from Karen in Yorkshire Water, if there's a microphone near her. So we're all water companies are starting to go on this journey, and I know, Karen, I won't say you do something different, but it'd be good to just pick up about the sort of, I know you said to me measured and unmeasured, so what's the approach there?
So yeah, I guess I think we're one of those companies who's got about 25% of low balances across our trunk mains. Obviously that varies quite a lot because there's a lot of DMA meters and they go down, so we actually have a greater number covered, but in any reporting month it's less. So when we went along this journey, obviously you want to reduce your unaccounted for water as well as reducing your trunk main leakage. So we had to take it really seriously in terms of our approach to measured and unmeasured. So we can be proactive or we can be reactive with the stuff where we do have data. But what we did do was a really systematic approach to all those areas which we don't have any data for. So that was surveys, lifting every lid, every fitting, and sounding and surveying every single one of our trunk main that aren't measured, and then repeating that process over and over again to make sure that we, as we reduce our measured trunk main leakage, we equally reduce our unmeasured trunk main leakage, so we're still accurately reporting based on the whole data set. And it's been a difficult journey. We have specific trunk main leakage inspectors to do that job, and we have to almost change their attitude, because they're not looking for a target of volume. They're just being as thorough as they can with their approach to finding those leaks. And just like Katie, I think we did get some really big wins, you know, in the early days, and we continue to do so, really. The lack of fittings is a hindrance at times, but actually it's those points of weakness where you do tend to see failure. So where you've got properties fed off your trunk mains, you know, the higher pressure just leads to failure on service pipes, comm pipes, guarded washouts, air valves, etc. So yeah, our trunk main team are really good at taking a kind of more open approach, a better attitude to kind of being proactive in finding those leaks, even though they don't have an absolute volume that they are looking for. I guess the other thing I would say is we have seen some wins where we've seen diurnal profiles. If you hark back to the paradigm presentation earlier, where you've seen DMAs that aren't fitting your paradigm profile, and then you've seen a diurnal profile on your trunk main balance, and so you know you've probably got a breach between a DMA and a trunk main, and that's obviously led us to improve operability in our DMAs as well as in our trunk mains.
Thank you, that's really useful. And I guess last water company view, Scottish Water, you talked about resilience and some of the techniques that you're using. Sweeps of trunk mains, walking trunk mains?
Historically, yes. I mean, I'm quite obviously old enough to remember pre-Scottish Water, pre-East of Scotland Water. We did have teams who used to walk the trunk mains every weekend, and you had set routes that people went out and did. Obviously, it's hugely labour intensive and expensive to do things like that. There are benefits to doing things like that. One of the biggest operational issues we generally have is you try and operate a valve on a trunk main or something and you can't get onto it, it's been tarred over or it's not operable. But if you had somebody going around regularly sounding it to check if there was any leakage on it, you would know that you would at least be able to access it. So we don't have anything that I'm aware of specifically at the minute. Obviously, if it wasn't clear, I don't work in leakage. I work in condition assessment. I wouldn't like to speak for my leakage colleagues on exactly what the plans are, but I know historically we have done things like that, yeah, but not for a long time.
Okay, fabulous, thank you. Thanks, Martin. Okay, right, let's move on. Last presentation from the panel from Dill. That's going to talk about data validation.
Sorry, I have to put my glasses on, too old. Okay, so I'm going to talk about data validation to produce the flow balances, what is required, and what are the challenges around that. So to produce the flow balances, the upstream network containing the trunk mains and the service reservoirs need to be defined and validated. So how do we do this? So GIS is probably the best place to start, because it contains all your assets. It should contain the connectivity as well, and all the consumption points. So we can analyse the GIS data to create a schematic, and that schematic can then act as a focal point to produce those flow balances. So in what we have here, oh sorry, that's jumped ahead now. So what we have here are polygons or zones, and within those zones you can see the traced network of the trunk mains. And if we zoom into one of these, see a bit more detail, you can see we've got 4 trunk main systems there, or sub-networks, as sometimes we refer to them as. And then you can see how that's been transformed into a schematic. So how do we achieve this? So what we do is we undertake a trace analysis of the GIS network. So we'll pick an upstream asset and we'll trace outwards to the extent to predefined boundary conditions. And as it goes along tracing, it's picking up all the assets on that trunk main system, it's picking up all the demand allocation points and all the closed valves. This is keeps jumping ahead here. Right, so the challenges. So unfortunately, your GIS systems can vary in terms of their quality, and because of that, you may have missing assets within your GIS system, so cross connections and valves and meters. You might have the presence of ghost assets, so you've got stuff in your GIS, but it doesn't actually exist in the ground. The status fields on your assets may be incorrect, so typically valves may be shown as open, but in reality they're closed, or vice versa. Or you might have assets shown in the wrong direction, things like NRVs. So when we're finding these issues, we have to go to the clients, speak to the network engineers, modelers, and try and get the best representation of the network. But this is just a first pass at this stage. And when we get further into the slides, you'll see why that's the case. So with the schematics created, we can then start defining the tiles. So the tiles have a supply meter or supply meters acting as an inlet, and then they will have a combination of outlet supply meters, district metered offtakes, demand offtakes, so that's the properties that are straddling along the trunk mains, not the DMAs. If there's service reservoirs contained in the network, you need to account for them. Large metered users that are logged off the trunk main, and any closed valves. Sorry, the slides keep jumping there, I apologise. So we've got a representation of a schematic here, and we've done this analysis in terms of defining what the tile should look like, and we have two represented there, a trunk main tile and a service reservoir tile. So it should be pretty easy to do that because you've gone through the GIS, you define the schematic. It should just be now a case of looking at your monitored data for your meters and your service reservoirs to set those up. But there's challenges around that as well. So you might have a meter in your GIS, you jump into your telemetry system, and that asset doesn't exist. So you have to modify your tile. There may be mismatches in terms of what you've got in your GIS system and your other corporate systems. That happens all the time. So it may be called, I don't know, high street meter in one system, and it might just be high in the other system. You need to also take into account any operational changes. So you may have valves that are operated on a seasonal basis to manage your supply demand. So you need to potentially combine those tiles when you get that situation. So once those tiles are established, we can then use the flow balance approach to produce discrepancies. And they're between the supply flows, the demand offtakes, and any change in storage along the tile. And so if you look in the top left-hand corner there, we've got discrepancies showing there for a number of regions, and they're ranked with the highest discrepancy on the left, going down to negative ones on the right of that graph. And then in the donut, we've got an aggregation of all of those discrepancies. We can also then apply an operable or non-operable status to those discrepancies. And we do that by calculating some key metrics. And so in the bottom half there of that dashboard, you can see that there are 4 scoring mechanisms that we're using. And again, they're ranked highest to lowest. And then there's an average score in the donut. So what we're looking for is a high score. This is a tile that's got a high score, and that indicates that the discrepancy can be targeted for detection and repair, and then you can also use it for potentially for regulatory reporting. But what happens when you haven't got a good score? You don't trust the discrepancy that you've got in there. So there's a number of things we can do in terms of the validation. So we can validate the discrepancies. So this might go back to the schematic. You might not got the connectivity quite correct when you originally did the definition of those schematics. You might have consumption points that are not connected into the trunk main network. So we've got a warehouse there that should be connected to that main. So you need to account for those. You may have genuine leakage, but you're probably not too confident at this stage. So you look at another one of the metrics. So you look at the availability and reliability of the data. In this example here, we've got some missing data. And in this instance, we've had to estimate because there's an issue with that particular monitoring point. On this one here, we've got a site that's dead banding. It's topped out for whatever reason. And so again, we have to consider estimating this value of this meter, sorry. We need to be able to trust all the meters. And so we promote doing meter verifications on your meters. And so we do a lot of that, especially on the DI meters. But if you want to get to the point where you can target the tiles, then you need to move that into the interzonal and tile meters. You need to go and check the boundary valves as well to resolve any integrity issues. So you may have valves not correctly identified on your tile, so you need to go out and check those. But when you go to do that, you may find that you can't locate the asset. There's vegetation that's overgrown and it's covering the access to the valve. Sorry, I don't know why it keeps jumping, apologies. So here we've got an example of our guys going out and checking the valves, and they're taking some pressure recordings at downstream hydrant to help confirm that the valve is closed. Jump over that one. Finally, there's no point producing these discrepancies unless you're able to target the leakage within them. So the guys have alluded to it earlier. You need to make sure that you've got enough assets on the network. And if you've got enough assets, they're going to be located. And if you can locate them, they've got to also be usable. So it's important that you actually survey, as Karen said earlier, your trunk main network to make that assessment that they're ready to target as well. And this is just an example of us doing some correlations and finding a leak out on the network. Okay, so to wrap it up, it's a cyclical process. You don't just do it and then leave it and say, well, I don't like the look of that. I'm just going to leave it be. You've got to have iterations of looking at the data and improving it. So it's a cycle of management approach, and it's applicable throughout the reporting year. And it's got to be a long-term commitment. As Katie said, they've been at it for years and they're still finding issues. So it's a continuous process, no different to DMAs. It will require improved data technologies, processes, and competent trained people. That's something that you will need to review. Sorry, he's jumping ahead again. And you'll need to invest both operationally, in terms of people's time to investigate, but also capital investment as well. You may need to replace meters, or you may need to install new ones. But from that, we're going to get incremental improvements in your data sets, and that should help us allow us to make better decisions on how to manage the upstream network, and so we'll improve the performance of the network through that. And as a consequence of that, it should provide us a better basis for estimating the trunk main and service reservoir leakage at the end of the reporting year. And just to finish off, there's a couple of our dashboards that we're currently producing that our clients can use to help follow that process. Okay?
Thank you, Dill.
Sorry about that with the animations.
Thank you. Yeah, I want to move it on a little bit. So we talked a lot about process and systems. I want to talk about people. Katie, starting with you, you talked about dedicated teams. So are the skill sets, what about the skill sets for both the office analysts, desktop analysts and the field teams? Are they the same for DMA management or are they different? What's the story there?
I think to be an upstream analyst and to be a decent upstream analyst, it takes a lot better network understanding than it does for a DMA leakage analyst. You know, the great minds in this room have all iterated on DMA operability over the years. We've got rules in place around PCC and things like that that says this DMA is either operable or it's not. The flow profiles that you're looking at on upstream, they can look like a nice DMA flow or they can look like absolutely anything. And they may be right or they may be wrong. And so you do need to actually really understand how your network's working so then you can actually validate what is good data and what's not. So the upstream analysts do need a sort of higher level of skill set than a lot of the DMA leakage analysts. And that is always a challenge. And then actually out in the field, because of your lack of fittings, because of sort of having to do trunk main correlations and stuff like that, again, it's tougher than DMA leakage. You can train DMA leakage technicians relatively straightforward compared with what experience and what techniques you need for trying to do upstream. You're really wanting the cream of the cream.
Okay. Michael, Severn Trent, I know it's in particularly your area, but any thoughts from Severn Trent? We promote our demand technicians from our DMA targeting teams into the upstream analysts, don't we?
Yes. I think the thing that's worth considering is, as Katie says, often in Severn Trent, demand tech, which is kind of looking at the DMAs, targeting in the DMAs, is often the first job. It's where I started as a graduate. Thank you, go in there. I think when you put someone onto the trunk mains, you want them to have perhaps somewhat of a modelling background or somewhat of a networks background. So you wouldn't put someone there completely new. They need to have some grounding in hydraulics and in how networks work. So I completely agree with Katie. It's a higher level of skill that you need in that area.
Okay. And we were going to talk about, we had a question around modelling, hydraulic modelling, which we're a bit tight on time, so I'll leave that one. What about contract partners? So do we need to get our field contract partners up to speed? Is there a whole load of leak detection coming their way? Katie?
Yeah, I think there is a real need, and I think where we've been asking our contract partners to provide resources, they are struggling. There aren't those people out there, so that is a genuine gap in the market, really, because trunk main leakage is that much harder. Then the contract partners are really struggling to find people that they think will be able to actually be of assistance.
PS crowd, as you do this for certain companies, upstream, field, any views?
Yeah, we've got staff doing those more complicated surveys, but it does take time. It is that training, getting that experience with other people, that understanding how that network works. So it means that we see a lot of that, like Michael says about the network modelling. If you model that area, you know where the model tells you all the demand is. You've got some concept of that before you go out on site and look at the trunk. So yeah, I think it's a journey with the technicians, because obviously there's a period where some trunk mains won't get involved, so it's getting familiarity back to getting out on site and understanding those trunk main areas. And the tools available, there's lots of different tools that can be used, but it's finding the right tool for the right trunk main as well.
Yeah, we use we call them hybrid engineers. So they're normally graduates, but we will put them out doing field work on the trunk main system, and they'll normally work with a more experienced technician who knows a little bit more about the leak detection technology, but the engineer has the knowledge about how the network operates. We try and buddy people up in that way to try and be a bit more effective when we're doing that type of work.
Thank you, guys. So before we wrap up, are there any other questions? I've got one here on Slido, which ultimately gets to the nub of it. How quickly do you think the sector can move to trunk main balances, upstream balances? So I think Ofwat are giving us till the end of AMP8. Companies will go at different paces, I think, different pace. Any views, Ken, from what you see around your group?
I mean, from seeing what I've seen in the group, the companies I've gone and had a look at, there are some more progressed than others. There are some which are really at the start and really need to do a lot of work to even get to the basic.
Okay.
Demand data outside the DMAs is a big issue, and I think a big gap in a lot of those companies who are starting their journey. I think it'll be a push for some. Some will be there quite quickly. I think some will be a push to get there for 5 years' time. Okay. But it's achievable.
Any other questions before we wrap up? No? Okay, thank you. So I think from my point of view, thank you guys for that. Just in terms of my takeaway, so I think there's definitely a question around the definition, but the guidance. So I think we need more guidance around what are we reporting. Upstream imbalances, unaccounted for water, real losses, and I think those are different numbers. Very much like the AMP7 guidance, there's quite a lot of wording around DMA coverage, DMA operability, availability, and I think there needs to be something similar for upstream. There's a lot, and we've got conflicting views around how you set up the balances. There's a lot of data-led. There needs to be, as Karen very nicely put, about measured and unmeasured. I think we need different approaches that complement. Do feel from the what Dill presented that very much you're doing lots and lots of data validation. At the end of it, there might be some leakage. And it's unfortunate the leakage is at the end of it, but if you take the view that Karen shared, that actually you can just go out and sweep that and do an equivalent upstream balance and upstream detection. There's definitely challenges around skill sets and technicians and field resource and contract partners coming on the journey with us. I think ultimately though, we do, and I think Ian said that in his 2 minutes when he had the microphone, we need to start taking care of our upstream network like we do our DMAs. We've done DMAs for 40 plus years, and we need to give some care and attention to our upstream leakage. And I do believe flow balances are the way to do that, and I don't think we'd get that with BABE. BABE is for reporting, but I don't think it helps you understand your network. So thank you to the panel, thanks for your questions. Hand back to Jeff, thank you.
Brilliant. Thank you very much, Paul, for leading us through that discussion, and for all of the panelists, Ken, Dilraj, Ian, Michael, Justin, Mikhail, and Katie. That was brilliant and a great way to finish us off. So we did have a few more respondents to the poll, and I think today, although the numbers are not big, today we did get quite a different response to yesterday. So by my maths, 2/3 of people answered yes. Today, 1/3 no. So more optimism today, I think it's fair to say, even though the numbers were small. So that's good, and I think there's been a lot of reasons for optimism as we've kind of gone through the conference. So it is that time that I need to draw this to a close. I want to thank all of our speakers for their time in preparing their really insightful and lively presentations. You know, we had some great presentations yesterday focused on strategy and some of the really exciting research that's coming up, including from a couple of PhD students. And then today we've kind of got really into the kind of the nitty-gritty some of the operational aspects and the technology. It's been hugely inspiring. And a big thanks to all of you for attending to sort of help with the discussions. You'll be able to recap and share with your colleagues who weren't able to be here the recordings that the conference team will share with you next week, along with, I'm sure, some of the slides. We've got a final thanks to our exhibitor supporters. I think we've got a slide on that somewhere. Aqualogic, BioMad, CLA Val UK Field, Gutterman, Horizon Water Infrastructure, HWM, Avaro, SME Water, Suez, Synthetech, Technolog, Tetra Tech, RPS, and our media partner, the UK Water Report. So thank you for them. It's really appreciated. And again, thanks to the support that we had for the dinner and the pre-drinks reception last night from Horizon Water Infrastructure and Tetra Tech RPS, respectively. So thanks for that. Thanks also to the AV team for keeping us mic'd and for the venue team for keeping us refreshed. And a really big thanks, and I'd like you to put your hands together for this, to Judith and the Lodestar team for really fabulous organisation. There's a huge amount of preparation that goes on to organise a conference of this size, not just in terms of the logistics, but actually also in terms of the content, which I think has been really well curated. So Judith and team, thank you very much. And that leaves me just to say, I hope you all have a safe journey home, get some daylight before you leave. And I hope to see you at the 26th Leakage conference next year. Thanks.